Now let's take a look at how we can solve an exponential equation using either the ln or log. And then we'll end up estimating the number by plugging it into a calculator using the ln button or the log button. So we're going to solve this. 4 to the 3x minus 15 is equal to 0. Well, the first thing you do is get the exponential term all by itself. Isolate it. So add 15 to both sides. 4 to the 3x is equal to 15. Now, we can't have, in order to solve this, we need the x, or first the 3x, to be down at the base level. So we're going to rewrite this as a log expression, a log equation, and the 3x will be down at the base level. So when we write it like a log equation, we take log, the base is 4, of 15 gives you 3x. And now let's double check that. 4 raised to the 3x gives me 15. Yep, that's it. All right, so then we're almost done solving for x, but let's go ahead and do our work down here. Let's divide both sides by 3. So x is equal to 1/3. Remember, dividing by 3 is like multiplying both sides by 1/3. Log base 4 of 15. And if we plug this into the calculator, well, first, let's use the change of base property. 1/3 comes out front, and you can use either log or base 10 log or the natural log. I'll write it down as natural log. Remember, it's ln 15 over ln 4. All right, so this is the exact answer. And if you plug this into a calculator, you get x, and I'll use the squiggly equals for approximately equal to 0.651. All right, so let's do this on several more examples. Okay, let's solve. Maybe I can keep the recipe up there. Solve 10 to the 5x minus 2 equals 10. Well, the first thing we do is get 10 to the 5x by itself. And what did I do there? I just added 2 to both sides. Now let's convert this into a log equation, which will put the 5x down at the base level. So that would be log base 10, because 10 is the base of the exponent. So actually, I don't even have to write that, but I will. Log, if we leave the base off, remember it means log base 10. Of 12 equals 5 to the x. And let me double check that. 10 raised to this gives me that. And that's exactly what we have here. Okay, so next, I'll keep going to the right. Don't want to run out of room. Just divide both sides by 5 or multiply by 1/5, and we get x equals 1/5 log base 10 of 12. This is the exact answer, but we're going to plug it into the calculator using the change of base property. So instead of log base 10 over 12, sorry, log base 10 of 12, I'm going to do log or ln, either one. I did ln up here. ln of 12 over ln of 10. Log actually would probably be a better one to use, but you get exactly the same answer. So let's come down here. X is equal to 1/5 ln 12 over ln 10. The only reason I said log might work out better here, log of 12 over log of 10, is log of 10 is just a 1. But we're going to get the same answer. So let me plug this in. We get 0.216. And here I'm going to put squiggly brackets since I used the calculator to get an estimate. I had to round off digits. X is roughly equal to 0.216. That's accurate out to the 1,000th place, and I've rounded. All right, number 10. All right, let's get this isolated, the exponent term isolated. So 7e to the 2x. Adding 5s gives 63. And then we'll divide both sides by 7 to get e to the 2x equals 9. Once again, divide this by 7 to cancel that one out, and divide 63 by 7 to get a 9. Now let's write that like a log equation, because that'll bring the 2x down. So I could say log base e, which I'm eventually going to write that as natural log ln, of 9 equals 2x. So this is equivalent to this. Now divide both sides by 2 to get x by itself. So I will get x equals 1/2 ln 9. That means x is approximately equal to, using the calculator, 1.099. This is the exact answer. Oh, I didn't have to use the change of base property at all since we used natural log. We didn't have, when you have log base 10 or log base e, you don't have to do the change of base. All right, a couple more examples. All right, so let's rewrite this. I need the 5x minus 3 to come down to the base level, so let's write this as a log equation. And I would get natural log, because it's a log base e, of 50 equals 5x minus 3. So these two are equivalent equations. Let me double check that. Ln is log base e, so e raised to this is equal to this. And that's exactly what we've got here. So I have to add 3 to both sides. I'll get 5x equals 3 plus ln 50. I switched the sides. All I did is add 3 to both sides. And just my preference, I don't like to put ln 50 plus 3, just so nobody is tempted to say, oh, 50 plus 3 is 53. It's the number 3 plus the natural log of 50. And then we need to divide the whole thing by 5, so x is equal to 1/5, in parentheses 3 plus ln 50. That's the exact answer. You could distribute the 1/5 through if you wanted to, but it doesn't matter. I'm plugging it into the calculator to get x is approximately equal to 1.382. All right, we got one more problem to do. It'll end this video. Let's get e to the 2x by itself. So first, get 3 e to the 2x by itself. Add 5 to both sides, and we get 3 e to the 2x equals 21. Just added 5. Divide by 3, both sides, and that'll give us e to the 2x equals 7. Looks like we won't even need the change of base property at all on this one. Rewrite this as a log, and it's going to be ln of 7 equals 2x. Let's double check that. ln is log base e, so e raised to the 2x equals 7. e to the 2x equals 7. That's correct. All right, all we need to do to get the exact answer is divide by 2. 1/2 ln 7. And by the way, I hope you're never tempted to say this is ln of 7 over 2, because that's absolutely not correct. It's 1/2 times the natural log of 7. That's the exact answer. That's what I'll want you to do on a test, unless I say use the calculator. The approximation is, when we plug it into the calculator, 0.973. And that is solving exponential equations by first converting to a log equation.